All right, welcome. Just as a quick reminder, very important, we don't have any class on Friday. I will post a video for you guys to watch on logistic regression, and then we'll meet again next Monday. All right, so just as a quick, and I'll make it nice and bright here, reminder, no live lecture on Friday. Okay. I watch video or just read the notes if you want to, or just read the notes, or just the notes, or just read the notes on section 9.3, which is logistic regression. Okay. So that's a reminder. So, and if I can get my act together this afternoon, then I'll record that video and I'll have it posted before Friday, but otherwise it'll be posted in time for our regular class. So, right, no meeting on Friday, and then I'll just see you again on Monday. Okay. So I guess I should wish you a happy weekend at the end of today. Anyways, I'll see if I remember. Okay. So let's see here. What were we doing last day? I can't really remember. Section 9.1. Oh, right. Okay. So we've gotten into predictive data mining, which requires that we have kind of methods in place where, okay, if we're making predictions, then we need to make sure that the predictions that we're putting out there are actually good, right? So there's a multi-step process that we need to follow. So the first one, and that's the one we talked about last day, was, okay, so we have a data set, and typically we have a huge data set, right? And in order to build models to predict stuff, let's say, then we split that data set into 3 parts, ideally, depending on how much data we have. And we talked about different ways that we could do that. But in the kind of grand scheme of things, we split into a training set where we build our model, right? And we decide, and we build many, many, many models. And then we decide from there which our top, 4 or 10 or whatever models are. Then we take those models and we apply it to a validation set, okay? And so that's data that wasn't included in building our model, right? And so that's unseen data to the model. And that's where we see, okay, well, how well does it perform on the validation set? So today we're going to talk about performance measures, right? How well did it predict stuff? Okay. And by stuff, I mean the response variable, but I think can all kind of get behind stuff. So how well did it do its prediction? And then from the validation set, we're able to pick the best model, the one that performed the best on the validation set. And then what we do is we take that model to the test set, and that's where we test it. And that's where we're able to get these performance measures from. But we've used the same performance measures all along. But that's where we get the final performance measures, the ones that you would brag about to your friends. So let's see if I can recap that in an eloquent way here. So as a little bit of review, well, I'll say predictive, but really in any modeling, in predictive modeling, but I'll put the predictive in brackets. So in predictive modeling, we ideally we're able to split our data set into 3 parts. So in predictive modeling, we can we ideally, I'll put in brackets too, we ideally split the data into 3 parts. Right, the first one is the largest part. And we talked about, you know, how can we decide how big it should be? It depended on how many predictors we had, right? How many explanatory variables do we have? That type of thing. And so it should be the largest, and it should be and it's called the training set. And this is where we used to build and identify the top performing models. Used to build and identify the top performing models. Right. And I'll double underline the S on the models, because we take a group of models. We don't just pick one. We take a group of models and then we apply it to the validation set. And we even talked about scenarios where, okay, we pull out our test set, which is our final set. We randomly select a test set. And then one of the options was a one-fold cross-validation, where we would pull out one for a validation set, right? One observation. And then we build the model on the entire rest of the data, right? Excluding the test set. And then we put that one back in, and then we pull another one and randomly select our validation set, which happens to just be one observation. I think that's a really cute option. But usually we have kind of the bigger training set and then a smaller validation set and roughly the same size test set. Okay, so the validation set is apply the models to the validation set and identify the top performer. Right, and then on the test set, right, measure the performance of that model on the test set, which is again unseen to the model. Measure the performance of that model on the test set. Okay. So how do we measure the performance, right? So notice we haven't talked about how do we build models yet, right? We talked about, okay, how can I split my data set and what should I be doing? And so today we're going to talk about how do I measure the performance measures. And we're going to focus on classification models, which means that we're going to focus on qualitative or categorical outcomes, okay? Because for numerical outcomes or quantitative outcomes, we're just going to measure the error, right? Then we have this difference between the observed and the predicted, and then that's what we use, right? And there are lots of things that we can do there, but the classification is a little bit more foreign to us. It's intuitive, right? You would probably be able to develop these performance measures yourself, but here they are on paper. Okay, and then on in the video that I'll post for Friday, then we'll talk about logistic regression, which is a way that we can build these models for classification. Okay, so we're kind of getting to the actual model. We're, I guess, building towards it. Okay, so the performance measures. Oh, hey, it doesn't want to. Let me grab that whole chunk. Okay. So today, we will develop some performance measures. We will develop some performance measures. And then in the next section, we will actually build a model, right? And then in the next section, we will actually build models. Build a model. Oh, but I muddled my model. We will actually build a model. Right. So that means that this section assumes that we have a model already. 9.2 assumes we have a predictive model already. Only because that can be kind of confusing. Okay. So we're going to focus on categorical outcomes. And then there's a little blip at the end of this section where we will talk about numerical outcomes, but here we're going to focus on those categorical outcomes. Okay. So if we have a categorical outcome, right, then we have categories as our outcome variable, right? And so what we're going to do is we're going to focus on a binary outcome, right? Yes, no, but even something like, are you in first year? Yes or no, right? So then if you're in second year, third year, fourth year, it doesn't matter because then you're in the no section, right? And so it depends on the question, right? But pretty well, actually, any categorical variable can be reduced to a binary variable. And we've seen that with the dummy variables too, right? Where we assign a 1 if that's the category it's in, and a 0 if it's not, right? So we've seen that before. And we're going to focus on, and we're only going to talk about the two possible outcomes. So we restrict our attention to problems for which we want to classify observations into one of two possible classes, right? And we've seen that before. So we can extend these, but that's for a different course, right? Maybe a later course, or who knows? But this will serve you well most of the time. So as long as you're able to boil it down to a 0-1 situation, then you're good. Okay. And so if I say, okay, given this information, I predict that this outcome will, and let's talk about just briefly about the lone default or no default. So you're working at, a bank, let's say, and you're modeling for them. And they're asking you, hey, should we be giving this person a loan or what? And then, so all you can do is look at some given information and then make a prediction, right? Will they default or no, right? And that's going to be hinged on some probability of them defaulting, right? And so your prediction might be correct, right? Or it might be incorrect, right? And so what we do when we're evaluating the classification And remember, classification refers to categorical variables. Right, this is for categorical. Okay. So, right, there's going to be some misclassification rate. Okay, and so we understand that because, but given the information, right, there's a good reason for you to predict that this person would not default on their loan, just make it a little positive, right, or that they would default on their loan. Okay, and so what we can do is we can develop a confusion matrix, especially if you have data set or a data set where you've built the model and you're also able to check against maybe some other data. Okay, and I saw here, yeah, so here we build a model and we are able to check, and that's how we pick a model based off of our training set, right? But then when we're actually going to look at it, then that's when we use the validation set or even the test set, right? If we're ready to call it a day. But if we're still making comparisons, then we should be looking at the validation set. So what we'll do is we've got this model, and of course, we use the same performance measures on the training set, right? And then we bring it to the validation set. But what we have here is we're going to build a model and we apply it. And I know that sounds vague because we don't have the model yet, right? It's not until we've seen the model that we can say, oh, okay, I get it. It's going to give us some probability of being in class 1. Okay, so typically we're only interested in the class 1 category, right? Not necessarily only, but mostly interested in the class 1. Okay? So what we're going to have in our validation set, for example, is we're going to know if they were in the 0 class or the 1 class, right? And so here, let's say this is no default and they will default on their loan. Okay. Here are the folks I predicted would not default on their loan. Right. And then here are the cases. So again, usually we're concerned with class 1 because we want to know, hey, are they going to default on that loan? Because in that case, I don't want to lend them money. Right. And so so that's the one that we're most interested in. Okay. We're also a little bit concerned with, okay, if you thought that they weren't going to default, but then they actually did, that's not good either, right? So it kind of depends on the scenario. In this case, both are kind of equally bad, right? So we could look at a couple of different error rates. Okay, and so the overall error rate is, well, if an observation is in class 0, and you predicted that it's in class 0, well, that's a good prediction. There was no error there, right? So I'll put a little green box around that. Same thing if they're in class 1 and you predicted that they would be in class 1, that's a correct classification, right? So that's a good thing. That's a good job from your model. Okay. Then we can look at, okay, if they're actually in class 0, how many did I put in class 1? This number is pretty large here, right? And so I'll do it in red. This is a misclassification. Hey, it's looking all Christmassy here. Little Christmas tree colors. So what you do is you just go through and you make R count the number that you that were actually 0 that you predicted to be 1, for example, right? And so you can just count those observations, and overall error rate, well, that's going to be the 2 that you got wrong, right? And so what we do is we use these little subscripts on n, and we have n actual, and then predicted. There isn't a comma in there, but it seemed weird to not have a comma there. Okay, when it's just numbers, it's understood, right? This isn't 10, it's 1, 0. Okay, so the overall error rate, well, this is an error, right? If it's actually in group 1 and it was predicted to be in group 0, and if it's actually in group 0 but it was predicted to be in group 1, right? And so you would get there, right? If I told you that, hey, here's what happened, and really cute because it's called the confusion matrix. It's like, hey, what happened here? Your predictions are all confused. So so it's called the confusion matrix, which I don't know, for me, I think is really cute. And so so just looking at these numbers, ignoring this formula here, what if I had just asked you, what is the overall error rate? You would figure that out, right? You would probably end up adding up these 2 wrong ones and dividing by the total number of observations in the table, right? And so it's nothing crazy here. There's nothing you need to remember, right? Until we get into maybe sensitivity, specificity, hard to say, and so on, right? But for now, these error rates, they come relatively naturally, right? So what we would have is a data set that might look like this. Okay, oops. So what we have is the actual class, right? So it's either in group 0 or group 1. And so we have these, the actual outcomes. And then we don't have the predicted class because we're allowed to change the threshold. And so what we're going to have, our model is going to give us the probability of being in class 1. Okay, and notice that this data set is really just split across, right? So it keeps going here. In case it's not clear, sometimes it can be confusing. So here it keeps going to here, and this keeps going across there. So there's really only 2 columns. It's just not stretched across a huge page. Okay, so our model, our classifying model will return a probability of being in class 1 for that observation. Will return a probability of being in class 1 for each observation. Okay, so it doesn't tell us which class it's going to be. We look at the probabilities, right? And for example, if I'm told, or if I told you, the probability of them being in class 1 is 100%, right? For all of these first 1, 2, 3, 4, 5 observations, right? What would you do? If I told you, hey, I'm predicting that they're 100% going to be in class 1, you would probably predict they're in class 1. Why would you do anything else, right? And so these would definitely be predicted to be class 1. However, right, if we kind of focus on just these guys here, maybe I'll copy, right? And if I'll zoom in here. So here we would predict class 1. Okay. Probably the 0.92, or as well, I should say, because it's just 0.9. So probably the 0.9 as well. But let's just focus on these guys because they're illustrating what we're dealing with here, right? So my model is telling me 100% these are all in class 1. Great. But what happened? Here, it's true, I'm classifying 3 out of 5 correctly, right? But I'm also misclassifying 2 of these, 2 out of 5, right? And so here, this one's correct, and this one's correct, and this one is wrong, and this one is wrong. Okay? So just focusing on those 5, right, we would have an error rate of 2 out of 5, right? Okay. So that's what happens, right? And so it's important because it can be confusing, right? You think your model is going to give you just the class that it wants to go in, but that's not what it does. It gives the probability of being in each class. And then we use those probabilities. So how do we pick some cutoff values? I guess I skipped down here. I jumped ahead. I got too excited. But I also feel like the class 1 error rate and the class 0 error rate is kind of obvious. So let's see here. See if I can bring this in here. Okay, how do I, there. So what we could do is we could go through and we could calculate the overall error rate. And if we took 1 minus that, 1 minus the overall error rate, that's the accuracy of the model, right? How many were correctly classified? Okay. Correctly classified, that's the accuracy of the model, right? Also, I think something that you would just arrive at, right? If you had to come up with a word, you would probably end up landing on accuracy, right? So there's really no terminology that you need to memorize quite yet, but we do need to have a good understanding of what they are, right? So there's usually an asymmetric cost in misclassification. For example, to a bank, if you say, hey, I predict that they're going to default on a loan, well, if you've made that prediction, then they wouldn't give the loan, right? And so that's playing it safe, right? And so, oh, I just got a private message, but if you could send me that in an email, that would be probably better because doing something else. Okay, so, okay. What was I saying? Let's see here. What was I saying? I was distracted. Oh yeah, so if we have declined the loan, then it doesn't really matter if they were misclassified to us, right? As the person loaning money, yeah, that makes a difference to me, right? I don't want to be misclassified because of some of my attributes, but that's a different story. From the bank's perspective, I've played it safe. I didn't lend them any money, so it doesn't really matter, right? But another concern, the main concern here is if I have loaned them money because they were predicted to not default on their loan and then they ended up defaulting on their loan, right? that's a concern to me. So there's these asymmetric costs in misclassification, and they depend on the data that you're looking at and the scenarios, right? So there's no umbrella situation here. But what we have is we can define the class 1 error rate, right? So how many were actually in class 1 but were predicted to be in class 0, right? So here, this is actual equals 1 and the predicted equals 0. Okay. And then here, remember, N11 is actual 1 and predicted to be 1, so that's good. And here it's actually 1 and predicted to be 0. And so in both these scenarios, it's actually equal to 1. And so that would be your class 1 error rate, right? They were predicted to be zeros, but they're actually ones. What percentage of those happened? And then same thing for the class 0 error rate. Okay. So what happens is, well, we can change that. So we saw that, okay, if I go through this table and we've sorted them by the descending order of the probability of being in class 1. And so what we could do is, well, based off of these probabilities, I might say that just as a jumping off point, if the probability of being in class 1 is more than 0.5, seems reasonable enough, right? Then make them all predicted to be in class 1, right? It's not true, but that's my jumping off point, right? And so in that case, we would jump off and we would say here, every point above here would be predicted to be in class 1. And so here, if the cutoff is 0.5, right, then these would be predicted to be in class 0, and these would be predicted to be in class 1. Okay. Okay. So we could adjust the cutoff point, right, to try to figure out, okay, where are my predictions kind of optimized? Okay. So right, the default cutoff value for a classifier is 0.5. Seems, pretty reasonable. But what we could do is we could, if we modify the cutoff value, then what we're doing is we're going to end up changing the class 1 error rate and the class 0 error rate. And so it depends on which is the worst thing that can happen to us, which is the worst of the errors, right? Worst of these two errors. And so as we decrease the cutoff value, right, more observations will be classified as class 1. Right, so here's our default cutoff at 0.5. Notice that we have all of these data points up above it, right? And then the rest are class 0. Okay, those are our predictions. Now, if I decrease the cutoff maybe to 0.3, so if the cutoff equals 0.3, I'm including 0.3, and you would just make a note of that in your analyses. I'm pretty sure it's up to and including 0.3. So that's why I'm including it. So, but I can't remember. Then these would all be class 1 and the remaining would be class 0. Oops. Okay. So let's see here. Oh yeah. So more observations will be classified as class 1. We've seen that, okay? Which also increases the likelihood of misclassifying a class 1 observation, right? And so the class 1 error will decrease. Right? Because you're putting more into a class 1, and so if there are class 1s, right, then we're good to go. Notice that as we have these low probability of being in class 1, so the probability, which means, right, if we only have 2 outcomes, the probability of being in class 0 is much higher, right? It's 1 minus this. And so here, if we have a look at the actual values, there's only one value that's actually 1. So it would be misclassified as a 0, right? But all the other ones are correctly classified as zeros, right? And so so it's hard to adjust our cutoff to include all the ones in the 1 category without having too many zeros going into the 1 category as well. So oh yeah, that's what I just said. So when I decrease the cutoff value, right, I am including all my 1s or potentially all my 1s in the 1 category, but I'm also throwing in a bunch of zeros that I don't really want in there, right? Okay. So what we can do, and maybe what I'll do is I'll grab this one first. We can visualize this trade-off. Okay, so if we have the class 1 error rate in the blue, and then the class 0 error rate in the red, well, at some cutoff value, so let's say 0.5, then we're going to have some class 1 error rate and some class 0 error rate. So notice how as I increase the cutoff value, right, making it harder to be in class 1, right, or to be predicted to be in class 1, well, then my class 1 error rate, it increases, but my class 0 error rate decreases. Okay, so in this case, you want a low error rate. Gets confusing, but this is just a little visualization of that trade-off, right? As we vary the cutoff value. We haven't I have mentioned it, but not on paper. So as we have mentioned, no, but I have talked about it, right? Identifying class 1 members is often more important than identifying class 0 members, right? So from the standpoint of the bank again, are you going to default or not, right? Because I don't want to lend to you if you're predicted to default, right? And then we are concerned with, okay, they weren't supposed to default, but then they did, right? We're concerned with that, but that's a risk that we're taking. Okay, and so what we want to do is we want to compare our model, right, or our classifier, because it's categorical, but it is a model. We want to compare it to how well we would have predicted things if we just randomly predicted class 1 or class 0, right? And so the cumulative lift chart does that. And so to gauge a classifier's added value added to, so compared with random classification, okay. A cumulative lift chart, let's grab it here. We have one to look at, of course. And maybe that got confusing. I won't do that there because it's here. Okay, so here's the cumulative lift chart. Oh, don't want to draw over the legend. Okay. So the cumulative lift chart compares the number of actual class 1 observations that were identified as class 1, right? If we look at them in decreasing order of their probability of being in class 1, right? So we have that list. And so what we're doing is we're looking at, we look at the cumulative count. So the count of class 1 records, right? As we go through an increasing number of cases, right? And so what we would do is this red line is if we were just randomly classifying as 0, 1, okay? And so what we're looking for here is the lift from this diagonal line, okay? So here we are looking for the lift, or for a lift from the diagonal line. We can take these values, we can take these actual ones that we see, and then we can divide them by how many we would predict to see just if we were randomly selecting. And that's what gives us this decile-wise lift chart. I don't know. So this decile chart, what we're looking for here is we're looking for high bars, okay? Which means that the ratio between the predicted ones, or the predicted ones, the correctly predicted ones divided by just randomly predicted ones should be high. Yeah, I've got that in a blurb, so don't worry. There. So we still order them in decreasing probability of being in class 1. So just like that table that I showed you. And then what we do is we break them up into groups of 10, right? Starting from the top. So groups of 10, and then we look at, okay, how many class 1 observations did I have? And there's a lot kind of explaining how to get to this graph here, right? How do we get these bars? But the key thing is being able to read it, right? Usually R just has built-in functions that will generate these. Okay, so once you have a model, then we'll just generate these. So that's not the problem. The problem is, of course, interpreting these, okay? So let's see here. Here, this is the one I wanted you to take home. The taller the bar in a decile-wise lift chart, okay, the better the classifier is identifying responders in that group. Okay, and so there's a huge explanation, but what we do is we take the values from here and we divide them by the values, the y values on the red line, and that's how we get these bars. Okay, so we don't need to generate these. Well, we do, but using software, right? But we do need to know, okay, I'm looking for the larger the bars or the taller the bars, the better. Okay. Okay, let's see here. Now we're going to get into a little bit of terminology to maybe not memorize, but be aware that there are these different terms and they mean different things, right? Every word we say has meaning, especially in statistics or data science, of course. And so every little word counts, okay? So what we can talk about, right? We've got the class 1 error rate, we've got the class 0 error rate, okay, and the overall error rate, of course. And so what we want to do is, well, what if we want to know how well it was predicting class 1 observations, right? And so the ability to correctly predict class 1 observations is just 1 minus the class 1 error rate, right? And so the sensitivity or recall, but usually we just call it sensitivity because then there's specificity, right? And so the sensitivity is going to be 1 minus the class 1 error rate. Okay, so it's kind of the opposite of the class 1 error rate. Okay. So basically, how many did I get right? Right? How many of these class 1s did I get correct? So as long as you remember that, then the term sensitivity, specificity, not so much. I can't get there, but you just need to keep track of 1, right? And so the sensitivity is basically how sensitive my classifier is to picking up on class 1 observations, right? At least in my mind, that's how I remember the term. Okay, so here I think of sensitivity as how sensitive my classifier / model, because I often call it a model. I mean a classifier, but the model is a broad term, and then we have regression or classifiers that fit into both of those, or that they're both models. So usually I just call them models, broad term. So I think a sensitivity is how sensitive my classifier or model is at predicting class 1 observations. Right? Can it pick up on class 1 observations? So then if we want to look at class 0, so how well are we predicting class 0? So that's the flip side, right? Then we call that the specificity. Okay, so the ability to correctly predict class 0 observations is called specificity. And again, of course, we take the class 0 error rate, how many did we get wrong? And then we just want to look at, okay, well, then how many did we get right? And that's the specificity. Oops, highlighting all over the place. So we can calculate the sensitivity, we can calculate the specificity, and we can use those values, right? And that's, I find, no one has trouble with that. We can also talk about things like the precision. Okay, so precision is the measure that corresponds to the proportion of observations predicted to be in class 1 by a classifier that are actually in class 1. Okay, this sounds familiar, right? But what happens is, let's see here, the only difference is that when we talk about the sensitivity, right, which are the correctly classified class 1s, divided by how many were actually in class 1, okay, versus the precision is how many were predicted to be in class 1. Okay, that's the precision. Did you predict the whole data set to be in class 1? That's not very impressive. That's not very precise, right? And so, so the precision is slightly different. And of course, I'll try to. So this is the class 1 and predicted class 1s, and these are class 0s and predicted class 1s. So total predicted class 1, as opposed to here, this is the total actual class 1. Slight difference. Okay. So the precision is another measure that we could consider. And then the F1 score combines the two. Okay. And so it combines the precision and the sensitivity, right? And how it does it, I'm not entirely sure of the math, but it looks pretty straightforward, right? We've got N11, N11 in the numerator. So we have 2 N11 in the numerator in the F1 score. Okay. Over 2 N11, so 2 times the number that were correctly predicted in class 1, plus the ones that were actually in group 0 but grouped into group 1, and the ones that were actually in group 1 but predicted to be in group 0, right? So the F1 score you can play around with, but you really just apply the formula at this point, right? So just to keep it kind of even keel here, I'll highlight that as well. Right. So we're not going to talk about where this came from because I didn't look too much into it, but anyways, it's a combination of the precision and the sensitivity. So what we saw was that decreasing the cutoff value, right, is going to decrease the number of class 1 observations that are misclassified, because most of my data set is now classified as class 1. So I've decreased that class 1 error rate. But what we're going to look at is that was at the cost of increasing the number of class 0 observations that are misclassified, right? And so what this is called is an ROC curve, okay? And so we're going to build this receiver operating characteristic curve, so ROC curve. Okay. And what it's going to look at is that trade-off between correctly identifying class 1 observations, that's a good thing, right? But also kind of looking at, okay, well, how many did you misclassify into group 0 or from group 0 grouped into group 1, right? Because one obvious prediction, but very, very useful, or useless, I can't believe I said useful, very useless, is to put everyone in group 1. Done, right? Some of them are wrong, some of them are right, feeling pretty good, right? But that's that's not good. Right, and so what we have is this type of curve. Let me grab it here. So we're looking at the sensitivity. The sensitivity is how many were correctly classified into group 1, right? And then we're looking at it against the class 0 error rate, right? So we're looking at this trade-off between, okay, correctly classifying into group 1, right? If I'm putting everyone in group 1, then that's great, right? But also my class 0 error rate would be 1 as well, right? So that's not good, right? So we want to look at, okay, so the trade-off between, and this is just randomly assigning them to class 1 or class 0. And I'm gonna grab this here. Okay, bring that there. Let's see if I can kind of make this a little bit bigger here. Okay, so what we can do is we're going to look at the area under the curve here. Okay, and so and that's called the AUC, area under the curve. Area under the curve. So AUC is area under, and I guess I should capitalize under the curve. Okay, because that's not obvious there, but what we're going to find is that the greater the area under the ROC curve, so the greater the AUC, okay, the better the classifier performs. Yeah. So we can talk about why that is, but as long as we know that, okay, well, yes, we can Google our way. So at this point, I haven't shown you how to generate any of these. And to be honest, I'm going to have to brush up on it. That's okay. I'll do it for the video. And we can just Google our way to finding these graphs, right? It's really just a scatter plot, essentially, right? And so there's nothing crazy going on here. And so we can develop these ROC curves and the area under the curve. What we're looking for, and that's the important part today, is what we're looking for when we look at these here is we're looking for a large area under the curve. Okay. So that's good. Okay. So now we're moving on to estimation, and that's for numerical data, right? And so here, now we have these continuous outcomes, right? So we have these numerical outcomes. And before, when we had a classifier, we were predicting values, we were predicting outcomes, which class is it going to be in, class 0, class 1. And what you'll notice is that there's really not, I didn't include very much until we hit 9.3, which is going to be in that video, on the continuous outcomes, because there's so much in there that we'll kind of tackle it. And we already have some of the key measures, like the mean squared error, and then we're going to talk about the root mean squared error, but they're all hinging on the error terms, which we can calculate mathematically, right? Because now we have numerical outcomes that I can subtract, and all of a sudden I have this measurement of how wrong I was, right? And so, so everything that we do for continuous outcomes hinges on that error term, right? Which we've seen before, but let's see here. See if I can maybe go a little bit smaller. Okay. So here, let's see here, I want to highlight. So we talked about the MSE. We talked about the MAPE. Oh, sorry. I underlined the mean absolute error and then I said the MSE. I don't know, I jumped ahead. Sorry, that's the MAD. In that case, it's the MAE, but I prefer the MAD because it's easier to say and it's funnier. So there's that. There's the MAPE and the mean squared error. Okay. So those are some other tools that we can use, and those are the ones that we introduced initially. And so what we can do, we can still use those tools to evaluate how wrong we were for a continuous outcome, right? But everything that we do for a continuous outcome hinges on the error, okay? Right, and you remember that the error is the actual minus the predicted value, right? And so for numerical data, we can calculate how wrong we were. And that's the error. And it's the yi minus y hat or yi hat. So the error is the actual minus the predicted. Whereas remember before with the categorical variables, then they're either in class 1 or they're in class 0, and I predicted one or the other, and then it's either right or wrong. There was no measure of, oh, that one was really wrong, right? No, we didn't incorporate that. We had some probability, and the probability of being in group 1 might be low, right? But we don't look at it that way, right? We're either right or we're wrong. Now for numerical measures, now we can have some sort of measure of how wrong we were. Okay. So what we can do is, oh my gosh, copy. I slipped, deleted it, only temporarily. So if we have some average account balance, I think it is for 10 customers, then what we have is we have some actual average balance that customer has, right? We have some estimated average balance, and then we're able to take the actual minus the predicted or the estimated, and then we're able to develop this error, right? And for some of these errors, they're quite large. Some of them were fine, right? Positives and negatives mean something, right? If I have a positive 9 here, then, well, I can kind of base it off of my data here, but you could also think, okay, actual minus the predicted must have been an under prediction, right? Which it turns out to be true, right? The actual was 3793 and my predicted was 3784, slight under prediction. So here, what we see is if EI is positive, we under predicted the balance. Versus if EI is negative, we over predicted. That's probably not a good thing, right? And so ideally we have an error of 0, but that's not going to happen, right? And so we want to decrease that error, okay? And once we can take the sum, so we can look at the average error, that should be close to 0, right? We can look at the squared error because, again, we have this problem of, okay, if I add positives and negatives, then if we're doing a good job predicting, the sum of those should be close to 0, right? But if I square each of these, then I kind of ditch the negative, right? And so now I have these squared values that I can add up and I can manipulate, right? And so we can look at the average error, which is just the sum of the errors divided by n, of course. We can look at the root mean squared error. So then we square the error terms, we add them up, divided by n, and we take the root. Just like the name says, root mean squared error. Okay. So the average error is an estimate of the bias in a model's predictions. Remember, bias is the tendency to over predict or under predict. Okay. And so what we find is that if the average error is negative, right, then the model tends to overestimate the value of the outcome. And if the average error is positive, right, it behaves the same way as the individual errors, right, then we're tending to underestimate. Okay. I guess I would highlight all of this, but I'll kind of leave it, right? And so the average error, and maybe I'll use a different color here. The average error, which I don't know if there's no symbol for it. That's okay. The average error, which is the sum from I equals 1 to n of EI divided by n, exactly as you would find the average error, right? If I asked you to do it. The average error is an estimate of the bias. Okay, so let me see if I can. The average error provides an estimate of the model bias. Okay. The tendency to over or under predict. Maybe I should say or under predict. Okay. Okay. So what we can do if we have a continuous variable, right, we can look at all these measures and we can identify the best one. Again, the root mean squared error is the same as the MSE, right? It has the same units as Y. And if we look at these measures or others and we apply it to the model's predictions in the training set, right? Well, the problem becomes, okay, if I'm putting it on my training set, that's good. I built my model there, but that's just analyzing how well is my model doing in general from the data that I built it on. How good was this model at modeling what I gave it? Okay. Whereas if I actually want to measure the performance of the predictive abilities, right, then I need to apply it to a validation set or a test set. Okay. So where was that here? In estimating future performance, we're most interested in applying the performance measures to the model's predictions on the validation and the test sets, right? So you pick the model based off of how it did on the training set, right? That's fine. But then to actually look at the performance measures, then you're going to look at the validation set and then the test set. Okay. And so we've got these, if we look at, it's not calculated here in the table, but if we found the average error was negative 80.1, right, then what we're saying is that we're consistently overestimating, which is what we saw. We saw a lot of positives, a lot of negatives here. Haha, confusing, right? So we saw a lot of negatives here. So overall, it's a negative error. And so it means that we're consistently overestimating the actual balance. Okay. So if the root mean squared error of 774, now let me see here. What was our total? Root mean squared error is 774. And then I'm lost. Where did this 43% come from? I lost it. Oh, huh. Let's see, 774. No. Anyways, I've lost it. I can't remember what I was going to say here, but I guess the key part was this is the one that I'm kind of hung up on, this 43%. I'm not getting there. Was doing so good until the very end. Oh well, you win some, you lose some. So anyways, the 43%, I'll have to come back and kind of clarify. So I'll clarify before I post the notes. But the key part here is if we have a root mean squared error of less than 10%, then that's a good thing. So we're looking for a root mean squared error of less than 10%. In this case, it's 43%, so that's not very good. So we would try to find some other estimating model. Okay. Yeah, I can't seem to find where that 43 came from. So anyways, I'll leave it there and I will investigate, and I'll put a little note here. I will add the explanation before I post it. How about that? Unless it'll just come to me, but it doesn't seem to be doing that. Of the average, oh, actual balance. Right. $70 or 774 divided by the average actual balance, 3793. So we'd have to add these up and divide them by 10. So I'll do that here, and that is my explanation. But how about instead of doing that with you guys on the line, I'll stop that here, and you should get to 43%. If you have any questions, let me know. I got that private message, so I'll look into that. But if you have any other questions, let me know. And if not, I'll see you on Monday. And I remembered, have a good weekend, because I won't see you on Friday. All right, stop this here.